to thank everyone for letting us come and talk to the Renewable Energy Conference. My name is Connor Wood. I'm with Caleb Lind and Brad Weber. We are excited to share with you our work on algae farms. We know a few of you have concerns with renewable energy, but our objective is to show you how it can be a viable source in today's economy. The purpose of algae is to capture carbon from energy plants or refineries. You can use algae as a biofuel source, 58% oil, so you can turn it into diesel, and leftovers can be used as fertilizer. Today, we were able to find a model that showed how algae changed with varying concentrations. We wanted to improve this model by putting in controllers that worked to have a set point for the different concentrations, and we wanted to integrate new disturbances, and we wanted to find an optimal value for production rate. Shown below is the model interactions. To the left is our differential equations, and you have some functions in here like alpha A or FM that take into account things like sunlight or pH concentration. And the equations are shown here. This is general photosynthesis, and below is how you make more algae. Our control system is, we have 5 control variables: algae, CO2, nutrient concentrations, temperature, and level. And we manipulate those respectively with harvest rate, CO2 pumps, fertilizer flows, heat, and a water inlet flow. And the disturbances, there was already solar radiation as part of the model, but we wanted to include ambient temperature, relative humidity, and wind, and see how they affected our model. And we started out by creating an FOPDT model to see how our control variables changed when we manipulated the manipulated variable. In this example, we have a change in our inlet flow of carbon, and the response is recorded here with CO2 concentration. It's kind of hard to see, but the dotted red line is our FOPDT model when we found the best fit for it. And as you can see, it fits pretty well. Another example is the algae concentration. This might be slightly more important. The algae concentration and how it changes when we move around our harvest rate. And you can see, again, the red dotted line is the FOPDT fit for this process. These are some of our values. This is the FOPDT constants right here, and the associated PID constants given IMC tuning controls. And on the right, you see this is our stability column. Stability tests were done kind of interesting. The stability of the system actually changes with the algae concentration, and it actually gets less stable the more algae you try to have. What happens is if you over or under consume a product, that product can reach 0, or it can reach toxic levels, which has to be consumed stoichiometrically depending on the governing equations. So there's a range associated with different operating conditions, and a transfer function stability test would actually prove unreliable because of how nonlinear the system is. So our stability tests were conducted. We used different gains while using the disturbance variables to see how our model did. This is a example of an unstable gain for CO2 pump. You can see the CO2 is oscillating wildly, and there comes a point where the CO2 reaches a toxic level, and the system's unable to recover from it, and algae dies. Another example is fertilizer rate. As you can see, the fertilizer rate at such a high constant has very high oscillations, and eventually the system becomes unstable again. So we were able to optimize it, and we found that we were able to collect 56,000 kilograms of oil per year per acre. And to give you some perspective, that's actually a 130% increase of what the regular values are. And we did this by changing set points for algae and CO2 and nutrient concentrations, and setting PID controllers to try to fix it at that point. If we were to work on this further, we try to gather empirical data at the high concentration to see if our equations actually were accurate at such a high concentration. What could happen is that these equations change with changing concentration. We'd also like to set up a cascade system where algae production is the master controller and all of the other concentrations, CO2, sugar, and nutrients were the slave controllers. And that way you could better optimize your system. And then finally, we did not include any research on market data, so we don't know how this would compare with costs if operating at such a high concentration would double or even triple your costs, and how that would affect what you actually want to operate at. Thank you so much. We hope you enjoyed our presentation.